this graph here to the right, and I want you to tell me what you think this graph is. Hopefully you noticed it's not quite the same as this guy above. It looks to be a reflective type of symmetry, and it's not just any type of reflective symmetry, it's a reflective symmetry across that y-axis. Since it has a reflective symmetry across the y-axis, we can say, I'm pretty sure that's even. We're now going to go ahead and prove that thought by plugging in negative x. So I want to plug in f of negative x and see what happens. I'm going to do 4 parentheses negative x minus parentheses negative x to the 4th power plus 8. Okay, now I'm going to go ahead and deal with all of these guys. An even power here means that this guy is going to become positive. So that's just going to become 4x squared. Then this to the 4th power, negative 1 times negative 1 is positive 1, times negative 1 is negative 1, times negative 1 is positive 1. So that negative goes away, and we're just left with minus x to the 4th power. And then that 8 just hangs out. Okay, we can go ahead and compare now what we've gotten. What we've gotten here is 4x squared minus x to the 4th plus 8, which is the exact same as our original function, which means that we've just shown that f of negative x is equal to just your original f of x. It's equal to the original function, and so the function is even. I want you to think back to what I said at the very beginning of these notes. How can you use what you know about even and odd numbers to determine whether a function is even or odd? I want you to take a second and look at these two equations and maybe take a guess at what you think you could guess about a function being even or odd by what you know about even and odd numbers. I'll rephrase it because I think it's a little confusing. What can you say about even and odd numbers that is also helpful for even and odd functions? Okay, I look forward to reading those responses. I would like for you to go ahead and try a few harder ones. So taking what you just said potentially about like a shortcut maybe, I want you to think about what you're seeing here, and I want you to try this first guy on your own. This function is neither even nor odd. If you go ahead and plug in negative x, we'll know if we plug in negative x for the cubed, that's going to become negative x cubed. And then this negative 1 here with the squared is going to cancel out, and it's just left with negative x squared. It's not the same as my original function because we have a negative in front of the x cubed. So my next step to show is like, maybe it's equal to negative h of x, which means that we're just distributing a negative into my original function. Since h of negative x does not equal h of x, oops, I keep on wanting to do that, and it does not equal negative h of x, then we know that this function is neither even nor odd. Took up a lot of space there. Okay, I would like for you to go ahead and try this next guy on your own. Our first step is to always plug in negative x for our function. I've got an x cubed at the front, and then I've got an x squared minus 4 inside parentheses. Simplifying that down, I've got negative x cubed, the square root of x squared minus 4. That negative gets canceled out because of the squared. And so I'll notice that everything inside the radical stayed the same, but now we've just got a negative right out here at the front. So we know it's not the same as the original one, but maybe hopefully some of you saw like, oh, wouldn't that just be the negative version of my original equation? Why, yes. Yes, it is. Since g of negative x is equal to negative g of x, this function is odd. Okay, last one. Okay, so we've got to find f of negative x. That becomes 2x to the fourth in the numerator, and then negative x cubed plus 4x to the fifth. Fractions can be a little tricky, so I don't know if really any of you would potentially have known what to do next here. So we need to think about what are the patterns that we're seeing and what are we looking for. We're looking for either the function being exactly the same as it was before, which we can see here that it wasn't. And then the next thing that we're trying to think of is there a way when it gets hard like this, because this is a hard one, when it gets hard like this, is there a way to manipulate, or is there a manipulation already happening in this function to make it such that it's equal to negative f of x? So is there a way that I can factor out a negative 1 from this to make it like negative f of x? And the answer is that you can. In your denominator, if you factor out a negative 1, you could say that that's the same thing as negative 1 times oops, you cannot see anything I was writing. So sorry. So I factored out a negative 1 from the denominator here as a greatest common factor. And then when you're multiplying a fraction by a number, you can either multiply it to the top or you can multiply it to the bottom. You cannot multiply it to both, because if you multiply to both the top and the bottom, you're really just multiplying by 1. So if you're actually trying to multiply by a number other than 1, then that means that that number needs to either be applied to the numerator or be applied to the denominator. We took it out from the denominator and said, oh, that's just negative 1 times this function, which, hey, this function is, or this expression, I guess, is my original function. So that's really just negative of my f of x. So that means that this function is odd. That is where it can get a little tricky, but we're looking for things either being the exact same way or for them to be odd. And so trying to think about ways that we can manipulate it to double check that it's not odd. Okay, that's it. That's it for even and odd functions. A reminder, this will continue to pop up in your future years, so just be aware of that and keep this in a place where you think you can reference it in the future. The other thing that we wanted to talk about is something called piecewise functions or piecewise defined functions. It's a little bit extra to put in. It just needs to be put in somewhere within your notes at some point this unit, and so we're just kind of deciding to put it in here. Piecewise functions are functions that look like this. If you see something that has like a curly bracket situation and two different expressions that are representing the equation of the function, this is a piecewise function. I like to think of it as a Frankenstein function, a Franken function. So a Franken function or a piecewise function is a function where you've taken parts of one function and parts of another function and you've put it together in the same graph. And so what we do is there's this definition of the function 2x plus 1. You are going to use 2x plus 1, this specific type of linear function, when x is greater than or equal to 0. Or when you have x is strictly less than 0, you're going to use this part of the function. So it's this idea of like the certain part of the domain, you're using different equations to find out what those y values are. Your official definition, a piecewise function is a function with multiple definitions. By definitions here, we mean equations or expressions. So that's your 2x plus 1 and 3x minus 4. Those are two different definitions, each applying to a different part. Of the function's domain. So again, you have this definition, and this definition of 2x plus 1 is only being used if you're talking about any x values that are greater than or equal to 0. For instance, finding f of negative 2, your first thought is, oh, negative 2 is less than 0. And since we're talking about that number being less than 0, that means that we have to use 3x minus 4. So that means we have to use this equation or expression, technically, to solve for f of negative 2. So then f of negative 2 would be 3 times negative 2 minus 4. So that's negative 6 minus 4, which is negative 10. 0, f of 0. Since 0 is greater than or equal to 0, so it falls under this part of our domain, then we're talking about 2x plus 1. So f of 0 would have to be 2 times 0 plus 1, which is positive 1. So you're using two different expressions depending on what x value you're putting in. I want you to go ahead and find f of 3 on your own. Since 3 is greater than 0, it falls under this domain restriction. So since 3 is greater than or equal to 0, that means that we are using the expression 2x plus 1. So f of 3 is equal to 7. All right, we are going to plot this piecewise function together in class. So what I would like for you to feel confident on with piecewise functions up to this point is I just want you to feel confident on how to evaluate them. How do you find the f of 3, f of 15? We have been evaluating functions up to this point by plugging in variables like f of x or f of t, or sometimes we've done like what is f of t minus 5. And that won't really work with piecewise functions because it can't really fall under a certain domain restriction. And so that's just something to keep in mind, that we're really only evaluating it with numbers. Okay, so even odd functions, determining them from a graph, determining them algebraically, proving them algebraically, and evaluating piecewise functions are things that I want you to feel pretty confident on right now. If not, come to class ready with questions, and Mr. Serene and I would be happy to help.